Hey class, so this week we're talking about probability distributions. So last week we just talked about probability in general, and we tried to figure out problems like what's the probability of some event happening, and then we also worked into some questions that were like what's the probability of some event happening given some other event happening. These were called conditional probabilities. And we even talked a little bit about joint probabilities as well. We used contingency charts to solve these things. So we're going to take it one step further, and we're essentially going to call these contingency charts probability distributions, and they're going to be slightly different than what we did last week, but with them we're going to figure out some more interesting questions. So like here's some types of questions we might look at. What set of investments will minimize risk? What's the chance that an Amazon buyer will buy at least one book, right? At least one book. Whoops, that was supposed to be underlined. What's the probability of a typographical error in the first exam? I write. Okay, this one we will actually solve this one. According to U.S. Census, 1/3 of all businesses are owned by women. If we randomly select 25 businesses, what is the probability that 10 or more are owned by women? So these types of questions, we have to assume an underlying distribution of the probabilities. And so that's really all we're going, is we're going to talk about probability distributions. And the only real difference between a probability distribution and the distributions we've talked about in the past, in the last couple of weeks we talked about distributions, is that we've always used the word distributions to talk about the distribution of frequencies of things happening in the past. With probability distributions, we actually just make some assumptions about what we think the probability will be. So it's not necessarily based off of frequency data. It might be based off of frequency data, but we'll assume that the same probability will be sort of applied going forward. So in frequency distributions, we were concerned about what the distribution looked like in the past. Probability distributions, we're going to use to sort of project or guess what's going to be in the future. So it turns out that these probability distributions come in 3 different flavors: tables, charts, and equations. So we've actually seen these sorts of distributions with frequencies in 2 ways. So tables, these are just where we sort of find some bins. We make bins and write how often something would happen in the bins. So instead of how often, instead of frequency, we display probability. So we'll see this. We'll see an example in just 1 second what this means. All right, so that's a table. We can turn those into charts, which are really just like histograms, and they're really no different than a histogram we've seen in the past. In fact, we'll see a lot of different histograms. These are just a visual representation of the tables and the bins. And then the one that we haven't seen much of are these equations. So there are some probability distributions that we're going to run into that can actually be represented with equations, and we can plug in a few numbers, and from these equations we can figure out the probability of certain outcomes with just these outcomes, with just these equations. And this is really just for convenience sake. And then you'll see that some of these equations are sort of applied universally. And so if I talk about a certain distribution, then I can actually represent it mathematically exactly. And everyone across the world does it the same way. And so if I assume that distribution, everybody knows what I'm after. And those are all represented with equations. In our class, we're not going to do a whole lot with these equations. I'm going to point them out to you and sort of scare you with them. But that's about it. We're going to let sort of Excel and do the heavy lifting on figuring out what most of this stuff is. So let's talk about this word random variable. So a random variable showed up in your notes before watching this video. Is really just a way of assigning a value, an actual number to an outcome, and we'll see that there are 2 main types of random variables. First one is called a discrete random variable. A discrete random variable is really it just means it's a countable thing, right? So a random variable, we're going to here's an example, a discrete random variable x, right? We're going to say, how often does x happen? That's really what a countable thing is, right? So we might say, I'm going to flip two coins. How often do I see 1 heads, right? How often do I see 2 heads? That's a discrete random variable. It's a countable thing. All right, we call them discrete because they are, I can't have 1.5 heads. I either have to have 1 heads, 2 heads, or 0 heads. Like that's it. Discrete. No sort of in the middle stuff. And in the middle, we talk about continuous. We'll get to that in a minute. So discrete, here's an example. A discrete random variable x has an associated probability mass function. That sounds great. F of x, where f of x equals the probability of big X equals little x. I don't know what any of that means. I do. It's really just what I just said, right? Essentially that this x has a probability mass function, which means I can figure out the x with some equation, f of x, right? In other words, a discrete random variable, the probability mass function is just a probability. So that's the same as saying, instead of giving me frequencies, I'm just going to spit out a probability. So this probability mass function, PMF, that we'll actually probably hear a little bit more of, has two rules, and these rules should sound familiar. This should happen across any discrete probability distribution. The first rule is it has to be between 0 and 1, so there's no such thing as having a probability less than 0 or greater than 1. And if I sum all of these f of x's together, it has to equal 1. So I add up all the f of x's, it has to equal 1. We'll see this in just a second. A random variable x also has a cumulative mass function, also called the distribution function of x, and it's denoted capital F of x, where f of x equals the probability that x is less than or equal to some other number. So let's make this a little more concrete. So here's our example. So say you own a used car lot. Yes, my dream. Say you own a used car lot. Awesome. And you've been sort of collecting some data, and you have some probabilities of how many cars you sell on a given day, right? So we're going to say X. We're going to say, let's change colors a little bit. Let X, it's a random variable, be the number of cars you sell in a day. It's countable, so it's discrete. The number of cars you sell in a day. That's supposed to be a D. Sell in a day. All right? So that's what we're going to say X is. And we're going to say, for simplicity, you can either sell 0 cars, 1 car, 2 car, 3 cars, or 4 cars. So you never sell more than 4 cars. Just doesn't ever happen. So you have sort of used the frequency method and calculated your expected probabilities for each of these. All right? You looked in the past and said, well, from past data, I know that the probability of selling 0 cars is 0.20. So 20% of the time I can expect selling no cars, 20% of the days, right? I expect 30% of the days I can sell 1 car, 30% of the days I can sell 2 cars, 10% of the days I can sell 3 cars, and 10% of the days I can sell 4 cars. These f of x's, this is the probability mass function. That's it. That's all it is. You can see a few things. If I add all of these up, it equals 1, right? 2 plus 3 is 5 plus 3 is 8, 9, 10. That's 1. Add those all up, that's 1. These are probabilities, though, right? So if I can ask a question, what's the probability of selling 1 car? 30%, right? That's it. So in fact, let's write that down. What's the probability that x equals 1? Well, I just come over here and say, oh, there it is. 0.30. That's it. That's all we do. So nothing to it. But here's another question. So we might ask a question like this. What's the probability that x is greater than or equal to 3? Greater than or equal to 3. Well, this isn't that hard. Like, here's 3. Here's 4. That's greater than 3. So I can just add those two up. That's 0.20. So that's all there is to it. 0.20. And those are the types of questions we're going to run into. The last set of notes, or up here, talked about this capital F of x. So let's figure that out too. The capital F of x is really the cumulative mass function, which means anything that's sort of smaller than some x, right? So 0 or smaller, well, that's just 0.20. 1 or smaller, well, that's 0.3 plus 0.2, so that's 0.5. 2 or smaller, well, that's 0.3 plus 0.3 plus 0.2, that's 0.8. 3 or smaller, this is 0.9. And 4 or smaller, sorry, that's 0.90. 4 or smaller is 1. This is a cumulative mass function, capital F of x, cumulative mass. We'll see in a little bit that this becomes pretty important. in some sense. In fact, we could have figured this out. What's the probability of x is greater than or equal to 3? Greater than or equal to 3. Well, we have 0.90. Sorry, let's do this one. What's the opposite of that? Well, that's the same as what's the probability that x is less than 3? I could write that again as something different like this. Since these are discrete, I can write this as the probability that x is less than or equal to 3, less than or equal to 2, right? These two numbers right here are equivalent. The probability that x is less than 3 and the probability that x is less than or equal to 2. That's a 2 right there. Let me erase it, make it prettier. Less than or equal to 2. Let me show you why those are equivalent, right? So here's less than 3. So 3 is not less than 3. 3 is 3, right? So less than 3 is 2, 1, or 0. Less than or equal to 2, that's also 2, 1, or 0. So if I use this cumulative mass function, that's 0.80. So these both equal 0.80 from the cumulative. There it is, right there. Cumulative mass functions given to me. So if I want to figure out this guy, it's just 1 minus that, right? Probably x is greater than or equal to 3 is just 1 minus 0.80. So that's it. So we're going to solve these types of equations where we're trying to find the probability that x is some value or between some value. All right. I think we're going to stop right there.